Hi everyone, welcome to the session looking at the code requirements and calculations for the design of compression elements. So we're going to be going through the various details from SANS 10162 Part 1 and trying to understand what the code is trying to give us and what the calculations are trying to do. So as I mark up the sections below, I'd encourage you to make these notes in your code so that they can inform and guide you as you design structures. Firstly, we've got our maximum width to thickness ratio to classify sections. Now refer to our other video regarding what is a class 1, 2, 3 or 4 element. And for elements in axial compression, we're specifically dealing with a class 3 or class 4. So it's either 3 or not 3, i.e. it's 4. So either it does not experience local buckling or it might experience local buckling. That's class 4. So we have this table here to try help us define may something undergo local buckling. So as you squash it, could a local section somewhere along its length buckle? And so you have this B over T ratio. And be very careful with B over T. B over T refers to something that is experiencing buckling. So you go here, it is this distance divided by that thickness. It's this piece of steel, B over T. Or, for instance, if it is a web, web supported on both edges, it would be that section there that you are designing. And look at the different B values you use. So you're just looking at would some section along the way experience local buckling? And so when it does that, then would it experience, for instance, local buckling like that, or like that, etc., like that, etc. One thing just to be very careful of, this is a bit of a contradiction. Normally when you deal with a web, you deal with the height of the web, which is from the inside of the radius, because there's a radius where the two flanges join. This is the one exception. When you deal with a web and you classify the web, it's h minus 2tf times, well, minus 2 times the thickness of the flange. Normally h it would be minus 2r1. That is not the case here. When you deal with a web, it's height minus 2 times the thickness of the flange. So it's from inside to inside. This is actually different to the Eurocode and some other codes, but just be careful when you classify a I section. It's as shown here. So this B over T gives, does my section experience local buckling? Once we know that, we can start looking at the equations for the design of compression elements. And so here you'll see the main equation looking at what is the resistance. Now initially this might look quite strange, but if you think of a force or a stress is a force over an area, or a force is a stress times an area. So having a look at this, what you have firstly is a partial factor. So this is the fact that the steel might not be 355 or whatever grade we're using. So this is 0.9 factor we've got there. Then all this next section is a stress times area. So this is a resistance of short column. So if it did not experience buckling, that would be its resistance. And then this last term is a buckling factor. And this value is somewhere between 0 and 1, or between 0 and 1. And so if you have a very long, slender column, this end term will be close to 0. If you've got a short, squat column that doesn't experience global buckling, then it will be close on 1. So if you push on your 30 centimeter long ruler, that's quite thin, you push on that ruler along its end, you put it into compression, and it buckles very easily. That will be a value somewhere between 0. If you, however, take that ruler and you cut it now so it's only 1 centimeter long, your ruler, and you push on it, it won't buckle. It'll eventually get to the yield strength of the plastic of the ruler. And so that would be a short column. So then this term would be approximately 1. So long, short, and everything in between. This is an empirical equation, and we'll look at what the shape of this compressive resistance equation looks like in another video. But one of the things just to note is there's an N factor there, or an N value. That's empirically derived, so they've done a bunch of tests and fitted curves. It's 1.34. Use this unless you're told otherwise. There's only one exception, and I think there's probably 2 or 5 structures in the whole of South Africa who actually this applies to. For doubly symmetric welded 3-plate members with flame edges, oxy-flame cut, and hollow structural sections manufactured according to blah blah blah, hot formed or cold formed stress relieved. So if you do a lot of effort and form it carefully and stress relieve it, use a different N value. So you would have to specifically be told for a very special structure to use that. So if in doubt, you pretty much always use that 1.34. Now, in terms of deriving this buckling factor somewhere between 0 and 1, we need what's called our non-dimensional slenderness, and this is addressed in another video and looking at the derivation. But ultimately, one thing you can see, this relates a yield stress to an elastic buckling stress. So this is yield, this is elastic buckling. So this takes into account a short column and a long column, and then from that we can see, is it likely to buckle or not? And so something with a very low buckling stress, a very low Fe, 10 MPa, that means it will buckle, the whole thing will buckle sideways. It's your ruler when you push on it and buckle sideways very quickly. And so the relationship between when it'll buckle and when it'll yield, and these are both perfect, a perfectly uniform material that yields and a perfectly uniform material that buckles, what's the relationship with them? And that gives you this non-dimensional slenderness. So ultimately, this first guideline covers doubly symmetric sections conforming to the requirements for class 1, 2, 3 sections. So as I said, though, normally in terms of compression elements, you don't really actually get class 1 and 2. We typically deal with class 3, but it's doubly symmetric. So these sections don't experience weird buckling. So what do those sections look like? If I just draw out some typical sections, this would be a circular hollow section, a rectangular hollow section, square hollow section, rectangular hollow section, I-beam or H section, or I-beam. Those would be the sort of sections this applies to, a doubly symmetric. So there are 2 axes of symmetry each time. So each of those dotted black lines serves as an axis of symmetry, and this would then apply. And so you can see that for these sorts of members, they behave fairly consistently. They don't have funny twisting behavior and lateral torsional buckling, well, flexural torsional buckling, etc. So they will be governed by this first clause. But what happens if they are not? So let's now move on and start looking at different clauses. So torsional or flexural torsional buckling, torsional flexural buckling, factored compressive resistance of asymmetric, singly symmetric, and cruciform. So, or other bisymmetric sections not covered under 13331. And one thing I just forgot is it says in the section above, doubly symmetric sections which may be governed by torsional flexural governing, buckling. What does may mean? When do you apply this? And from reading the code, it won't be immediately apparent, but if you understand the buckling formula, you can see where this is. This is the cases where a member experienced torsional or torsional flexural buckling, and so why might it do that? It would have a low J, a torsional stiffness, a low CW, which is a warping stiffness, and or a high LZ, a high torsional length. And normally when you have a high LZ and low other values, you have some sort of weird connections that do it. So those would be cases, and it's very difficult just to know offhand if it would occur. You'd actually have to run the calculations in most cases. However, in general, if you have a doubly symmetric section, especially pretty much all the sections in the red book, it won't occur. But if you have a very thin section, perhaps it would start occurring. So coming back, well, firstly now we've got a doubly symmetric cruciform or axisymmetric section. So firstly, what is a cruciform or an axisymmetric section? Cruciform looks like a cross. That is a cruciform section. And one thing you can just picture, if you now were to put a compressive load on this, this is likely to twist. And so a torsional failure is possible with it. And so that's why you have to be a bit more careful with it. And then you've got axisymmetric sections. For instance, a Z section. A Z section would be a blipped purlin. And this is, if you fold it over about one axis and then fold it over about the other axis, then it's symmetrical. Once again, these sections are likely to twist. So they have a center there, which there are axes of symmetry around it. And so for these ones, you need to test for the least of FEX, FEY, FEZ. So this would be a major axis buckling, a minor axis buckling, and a torsional buckling. So torsional, FEX, it would buckle sideways, and then FEY, it would buckle in the other direction. So refer to some of our other videos where we discuss this, but I know this is one section that people often don't understand. So remember, FE is an elastic stress, an Euler buckling stress. Then for singly symmetric sections, so one axis of symmetry, very, very important, with the y-axis taken as the axis of symmetry. The lesser of FEX and FEYZ, a major axis buckling, and then a FEYZ, a torsional flexural buckling, and there it is. So here for instance, this would be a singly symmetric section with the y-axis as the axis of symmetry. Now, to be perfectly honest, I get very confused when I start running these calculations, because in the red book, you, for instance, will have this is your y-axis and this is your x-axis. Now you rotate it, and now your y-axis is there. And now you've got two y-axes, and then it's very easy to make mistakes. So what I suggest to students is call this y-primed. Just call it something different. You can call it whatever you like as long as it's different, so you can know that that is a y-primed axis and this is an x-primed. So let me just put this in a different color so you can see. So you rotate the axes, you swap your values around, and see to the worked example. Hopefully it'll make more sense when you see a worked example. But your y-primed is an axis of symmetry. So you swap everything around to be about the y-axis, and then also this now applies here. So when you run your calculations, you use the properties about these updated axis system. So be very careful. When you talk about x prime, your x primed and your y primed used to be your u and your v axes. So you're actually using u and v axes in your calculations, but to avoid confusion, I just call them y primed, etc. So y primed, x primed, then hopefully that will reduce the amount of mistakes you make, but it is very easy to make these mistakes. And so when it comes to doing these calculations, we've got various requirements here, and this is then for a flexural torsional buckling, a buckling about the y-axis, which I will call the y-primed axis when we rotated it. FEZ, a torsional failure. One thing you will see is once in a while you will design a section and it will have no CW value. So just as a rule of thumb, you can take that as 0 if not listed in red book. Your CW is a warping value, a warping stiffness, and if there isn't one listed, take it as 0, and this whole first term just disappears, and that's fine. Okay, then the rest of these properties, omega and such, they count for where is the shear center relative to the centroid. And so you would use these equations that follow to start quantifying that and determining elastic buckling. The last type of section we will look at is asymmetric section. So the elastic buckling stress is the smallest of this fairly long, horrible looking equation here. Well, firstly, asymmetric are not common. The main section that you will design which is asymmetric is an unequal angle. They are useful. There are not many other asymmetric sections you will design. You do find it popping up once in a while. For instance, we've been doing work on shipping containers where people are converting homes into shipping containers. And the corner columns of those sections are asymmetric. They have all sorts of different shapes, but then you may have some sort of asymmetric section you are designing. So not common, but once in a while. And what you have to do is you actually have to solve this equation. So you find what is FE, what is FEX, FEY, FEZ, and you can solve for all these values. So that's fine. Once you have those, you then either with a numerical method or a spreadsheet or something, you find FE. You find FE. And then you find FE and what value of FE will solve this equation. You may find 2 or 3 values. This is your elastic buckling stress. And once again, it's the same thing there. It's an elastic buckling stress. You push on this and it gets to a point where a perfect column with no residual stresses will buckle, and that will be your FE. So that takes you through then the design. And remember, first you say, is it class 3 or class 4? Then what is its shape? Is it doubly symmetric? Is it singly symmetric? And then you've got torsional flexural buckling. Is it doubly symmetric, cruciform, or axisymmetric? Then you've also got to check FEX, FEY, FZ. Or is it asymmetric? You've got to solve now for this long equation. If you do have a section which is experiencing local buckling, what you want to do with it is adjust its cross-sectional area. So for instance, if I have a H section like this, and it's made of long, slender webs and flanges, when I load it, it'll get to the stage that local buckling occurs. And to account for that, to make my life easier, what I'm going to do is just remove some cross-sectional area. Actually, let me draw this in a different way, and then you can see that you can apply this in different ways. I'm going to draw a horribly asymmetric section, and what we will do is classify this section, find, oops, it's class 4. Now we need to reduce the area to an effective area. And when we find this updated area, what we are finding is a new width. And so it used to be the full flange width would give me my compressive resistance. But now I have I'm going to call it B new. So for instance, there's that B we were looking at earlier. And then if I remove this area in the middle, B new equals B minus area in the middle. B minus red area, red width. So I need to find some new width, some new value, which removes this red area here and removes these. And then I can have, for instance, a B new 1, a B new 2, and then a 3, and even a 4th one if I really wanted to, if I really had some bizarrely shaped section. But this is just to illustrate the point. If you classify it and it was some really thin steel and you ended up with all of these having different classifications, you could end up with something like that. And so this is the equation here that gives us this updated V value. And why I'm calling it B new, because this is even more confusing. We've had a B, which is the breadth of flange, which is the total width. Then we've got a B in classification, which is half the width of the flange. Now we've got a third B. So we've already got too many B values. So I'm just going to call this B new, just so I don't get confused and realize that this is different to what I was dealing with just now. So this is B new. This is some updated width to account for local buckling. And so this accounts for the stress in the section and when it experiences local buckling. So what happens is I classify my section, I find it is class 4, oh dear. Now I see, will it experience local buckling? No, it won't, based upon this check. And then I will use the total cross-sectional area. If I, however, find that it will experience local buckling, I need to update the area, remove that little red section, and so we need to then apply this equation. So the limit, this is an updated limit. We earlier were checking b over t is less than some value, 10.2 or whatever what it was. You would find by using your yield strength. We're finding a new value here. That's what this limit is. We're just finding an updated limit on the section, and this is a property of the how it's supported, the stress in the section, Young's modulus. So it's very much a buckling problem. So firstly, K equals 4 for elements supported along both longitudinal edges, or 0.43. So here is my I section, and there we go. This you have seen in one of the other videos, but for instance, that is supported along one edge because there's only an edge there. This is supported along two edges, 1, 2. This is supported along two edges, and then this is supported along one edge. 4 for elements supported by both longitudinal edges, 0.43 for elements supported along one longitudinal edge. So a section which has supported top and bottom is far less likely to experience local buckling. So once you've got that, then you also need a stress. Now what stress? You're trying to design this section. So we are told F is the calculated compressive stress in the element using ultimate loads. So it depends on what you're doing. If you're just trying to calculate what is the capacity of my column, you actually haven't got a load. You're just saying what's the maximum load that this thing can carry. So there are different values you can use. Either you could use CU, so that is the compressive load on your column, or B, you can actually use the CR of class 3. Because what will happen when you design these sections, you'll see in the worked example, you design it as a class 3 and you can actually get to a compressive load and you go, whoops, I actually need to reduce that load now to account for this reduction in effective area. So you could use that value, you calculate it for class 3, you plug it in here, oops, it's failed, and then you will adjust your effective area to do it. So that's just one way of finding a stress to use. So where does my stress come from? You will plug that in there. Okay, so that takes us through effective areas and the likes. The last thing we want to look at is just a single clause in the code. Now think back to your ruler, and so now let's say you're sitting in class once again, you've got a ruler and you're going to load it up again, and you can hold it at the top and bottom, and you put a certain amount of load on it, and then your ruler buckles sideways about the weak axis, and it'll look like that as it buckles. But now you get your friend to hold it at mid height, so he comes along and he puts his finger here, and he prevents now your ruler from buckling. You push on it and then your ruler will look like that as it buckles. So how much force does your friend need to apply here? How much force does he or she need to hold the ruler with so that it doesn't move sideways? And this might seem like a really stupid, trivial thing because, a ruler is not going to carry a lot of load. But in reality, this can be a big deal. There was once a structure I designed and it had massive silos on it. And it had thousands of kilonewtons coming down. I can't remember if it was 5 or 10,000 kilonewtons on these columns. We had to make up special columns because the load was so high. And then we had floors that were bracing this column. And I forgot to specifically check, could the floor members carry this sideways buckling force? And then suddenly when the column was going up, I thought, oh, hold on, let me just go check that, because a small force, this is a very small force, but a small amount of a very big load is still, maybe it can buckle my floor. Thankfully, it was all fine. It wasn't an issue. But you will need to check this once in a while. And the simple rule is that if this force is Cu, the sideways force you need to apply, how strong your friend needs to be, is 2% of what you are applying and at buckling. So the force there, if you apply a force of 2% here, or if you can apply a force of 2% there, you will prevent it from buckling sideways. And so that is then the resistance. So bracing system, so this is something that can prevent buckling shall be proportioned to have a strength perpendicular to the longitudinal axis of the brace system in the plane of buckling, at least 0.02 times the factored compressive force at each point in the brace. So that will then, if you provide at least that amount of force, you are fine. In most cases, you don't really need to check this because the force is so low. However, when the force starts getting bigger, when CU starts rising, this may be something you need to consider. And then in the clauses that follow, you'll actually see a detailed way of calculating what is this 2% or not, but this is a sort of rough and ready approximation that you can use. Okay, with that takes us through the SANS guidelines and how to go about designing a column, and hopefully that's starting to make more sense, and then the clauses in the code are a little bit clearer to you. Thank you.